Hello and welcome to our Physics 212 Project 2. For this project, we will be analyzing the buoyant force. Buoyancy is an upwards force that occurs any time that an object is submerged, even partially, in a fluid. This force is equal to the force of gravity or weight of the fluid displaced by the object, at least in the event that the object is fully submerged. In this image, we see how the buoyant force acting on the swimmer in section A is the same as the buoyant force on the water without the swimmer in section B. When researching about the buoyant force, it seemed to resemble some similar concepts to what we've already learned about in Physics 211 about the normal force. Just like how a normal force is always present for contact surfaces, there is always a buoyant force present for an object in a liquid. A buoyant force will always directly oppose the direction of the force of gravity, whereas a normal force can sometimes, but not always, directly oppose the force of gravity.
Now we're going to look at the cause of the buoyant force. Compared to the force of gravity on a submerged object, the buoyant force can either be greater, meaning that the object in liquid will float or rise towards the surface. The buoyant force can also be less than gravity, which means the object will sink. And when the force of gravity is equal to the buoyant force, the object will remain at whatever depth it is at. Due to the force of gravity between two objects increasing as the distance between the objects decreases, there will be more pressure as you move down in elevation in the fluid, and there will be less pressure closer to the surface. Pressure is a measure of force divided by area, so an object in higher pressure will have more of a normal force on it by the fluid than an object in lower pressure. Consequently, when an object is submerged in a fluid in gravity, there will be a greater force on the lower part of the object than the higher part. This net upwards force on an object caused by the fluids around it is called the buoyant force.
Our current rigid body model for matter makes it difficult to consider fluids, as we would need to consider the normal force interactions between each molecule of a fluid. However, if we can change our model to include fluids, still using our previous knowledge of Newtonian physics to do so. This involves considering the force of gravity on a fluid as a whole, along with knowing that the force of gravity between two objects increased as the distance between them decreased. From that, we know that fluids at a lower elevation will have a stronger force of gravity on them than fluids at a higher elevation. As the molecules in a fluid will contact each other while remaining relatively stationary, we can extrapolate that to know that there will be increased normal force interactions between molecules and an overall increase in pressure at lower elevation. This pressure gradient causes the difference of forces in the previous slide. Now, with these changes to our model, we can begin to understand the buoyant force. Our new model for buoyancy does, however, have some limitations. These limitations are mainly that our model assumes that the object in question is free floating in its fluid and not being supported by an external force. So an object on the bottom of a container likely wouldn't interact in the way that our equations would expect them to. Additionally, our model assumes that there is a pressure gradient caused by gravity in most situations from Earth. So if we were in a low gravity environment, our model would cease to work for our situation.
As we previously related buoyancy to pressure, we can also relate it to density as they have a direct correlation. The measure of an object's density and the density of the fluid it is interacting with can help determine the state or movement of the object. The mass of an object and the distribution of that mass over some volume can manipulate the behavior of the buoyancy force and the object being acted on. Examples of this occur in real life every day, from an object floating on water to a balloon rising in the air. These are the principles that we're going to use to examine these real-life scenarios as they involve fluids acting a force on an object, such as Archimedes' principle, the density equation, and the relationships of the density of an object versus the density of that fluid. The two main examples we want to examine today in real life is the movement of a hot air balloon and the interaction of a steel ship. When it comes to the hot air balloon, people directing the hot air balloon control whether the hot air balloon goes up, down, or floats in the air. They manipulate this by changing the temperature. The buoyancy force that depends on the density of the hot air balloon in relation to the density of the fluid it is floating in, or the air, can be manipulated or changed by changing the density of the hot air balloon and changing that density by changing the temperature of the air in which it's interacting with. The increase of temperature causes the density of the air to expand and ultimately for that density to decrease as the volume decreases. This then increases the buoyancy force and causes the object to rise. Vice versa, the decrease in the temperature causes the density to shrink down and the buoyancy force ultimately decreasing, leading the balloon to sink in the air. When the density of the fluid is greater than the density of the object. When the densities equal each other, that is, the density of the hot air balloon and the density of the air, the object should ultimately float. When it comes to the steel ship, one would question the ability for that object to remain on the water, as the density of steel is about 8 times greater than the density of water. An object with such mass would need a small volume in each part of the ship to counteract the differences in densities. The shape of the ship, however, allows for such an object to accomplish this. This would not be the same as if we took a steel ball of equal mass to that ship and put it on the surface of water, as the volume in which it distributes that mass is much smaller. If both the ball of steel and the ship of steel were to be put on the surface of water, we'd expect the ball to sink considerably fast, as their density would be much larger. While they have the same mass, the distributed mass over a smaller volume of the ship allows for a smaller density of the ship overall in comparison to the density of water. Ultimately, since the density of water is less than the density of the ship, this explains how it is able to float. These principles allow us to examine and explain these real-life scenarios and interactions because of the interactions of the objects and the buoyancy force acted on by these liquids, or fluids rather.
Now we will be looking at the sense-making of a buoyant force. In the situation shown above in Figure 5, a coin with an unknown density is measured in air, which is shown in Picture A, and then is measured when submerged in a liquid with a known density, which we see in the image B. In this experiment, when the coin is weighed submerged in water, it seems to have its weight be lost. This is because of Archimedes' principle, and that says that the buoyant force equals the weight of the fluid displaced by the object. And the buoyant force points upwards from the bottom of the object, and this upward pointing force would oppose the scale that is measuring the mass. Relating this concept to a real-world situation, we could look at when we go to the grocery store and put our produce on the scale. In this situation, if you push up on the scale from the bottom, the scale is going to read that the weight is going down and there's less weight being weighed than there actually is. In this situation, your hand pushing up on the bottom of the scale is like the buoyant force in the coin situation. The force is pointing upwards and relieving some of the weight that is being weighed. For all of our information on this topic of the buoyant force, we looked at the OpenStax textbook of Archimedes' principle and buoyancy.